everybody. Welcome to GATE online classes on reinforced cement concrete and pre-stressed concrete. So today our main discussion is on pre-stressed concrete. So in this primarily there are two different topics. One is analysis of pre-stressed concrete and another one losses of pre-stressed concrete. Only these two topics are there in the syllabus of GATE. So till the last class of around 7 classes, we have completed the entire reinforced cement concrete. Mala start cheyamantarama? Okay, till the last class we have seen several topics in reinforced cement concrete structures. Now it is another topic subject in concrete, which is pre-stressed concrete. And two major topics are there: analysis and also the losses in GATE syllabus. And our focus is only on these two topics. Pre-stressed concrete. So here understand the name of it, pre-stressed. So that means the stress is being introduced before the application of the load on the structure. So before the application of the load on any member, the stress induced in the concrete member, then that is called the pre-stressed concrete. So stress induced prior to the loading. So here because of this concept, lot of improvements are there and was recognized by the French engineer Freyssinet. So you can call Freyssinet is the father of pre-stressed concrete. And the major difference here in RCC and pre-stressed concrete is, in RCC we are providing the steel reinforcement to take care of all tensile stresses that are induced on the member. Whereas in case of pre-stressed concrete, our main motto is introducing the pre-compressive stress in the concrete. Introducing the pre-compressive stress in concrete. You know, concrete is very strong in compression and extremely weak in tension. And to take care of all tensile stresses, steel reinforcement is being used in RCC. In this case, instead of resisting the tensile stresses, we are introducing the compressive stress in the tension zone. We are introducing compressive stress in the tension zone, so that after the application of the loads, the tensile stresses that are developed will compensate the already introduced compressive stresses, so that the resultant stress will be well within the limits. So that is the main motto and concept used in the pre-stressed concrete. Pre-stressed concrete. So here, pre-stressed concrete is a basically concrete in which internal stress of suitable magnitude and distribution are introduced, so that the stress resulting from external loads are counteracted to the desired degree. So initially the concrete is induced with the compressive stress, and after the application of the load, the same face or the same face is subjected to tensile stresses, and these two will get balanced, and the resultant stress will be very nominal. It may be a small magnitude of the compressive stress, or maybe zero stress, or with the small magnitude of the tensile stress that the concrete can be able to resist. So that is the idea. So here you can look at the diagram. So here a cylindrical box is made with the wood, and these are the several wooden pieces, vertical lines separated the all wooden pieces. And if there is no band at the top, middle, bottom, etc., there is no band. And if something is kept inside the cylinder, naturally because of the hoop tension, all these members gets separated out. So what normally we do, the main purpose of this will be to store something, and because of storing some material, that material induces hoop tension in the structure, and it is going to fail because there is no resistance, hoop resistance. So to improve the load carrying capacity of it, what we do is we are applying the bands, we are putting bands by applying the tensile force in the band so that the compressive stress induced in the cylinder, compressive stress induced in the cylinder. And after putting something in the cylinder, the hoop tension will develop. The hoop tension and already compressive stress induced in it will get balanced or with a small magnitude is the residual of the stress, and that stress can be withstand. That stress is well within the limits, and the entire member is in safe limits. So here you can look at the precessed concrete normal beam. Here all these are the steel reinforcement used for pre-stressing steel. The main purpose of it is not for the resisting the tensile stresses. It will be useful for introducing the pre-stress in the member. Introducing the pre-stress in the member. Okay. Now, let us see a simple difference between RCC and pre-stressed concrete. In RCC simply supported beam, the bottom face is under tension, whereas the top face is under compression when it is subjected to transverse loading. When it is subjected to transverse loading, you can look at compressive phase and also the tensile phase. And concrete is very strong in compression and weak in tension. So what we are doing, we are putting steel reinforcement. We are putting steel reinforcement on the tension phase. So this is the area of the steel reinforcement AST. And already I have seen the stress diagram and the strain diagram and also the stress diagram. Whether it is working stress or limit state, okay. So the compressive stress at the top C, tensile stress at bottom, and main purpose of it will be to resist all the tensile stresses that are induced on the tension phase. Whereas in case of pre-stressed concrete, by introducing the pre-stressing cable, a pre-stressing force is induced in it. Pre-stressing force is induced in it, P. It is with an eccentricity of E. So, because of the direct force, the stress will be something P by A, which is totally compressive in nature throughout the cross section at any point along the member. Along the member at any point, the stress is uniform. It is because of the load. And because of the eccentricity, the bending stresses will also induce because of the pre-stress. So it is totally compressive, and that will be tensile at the top and compressive at the bottom. So that means by using pre-stressing steel below the neutral axis, we can increase compressive stress at the bottom. We can increase the compressive stress at bottom. So you can look at here the compressive stress because of the direct force P and also bending, it is C only. So what is the resultant stress at the bottom? Resultant stress at the bottom will be sum of these two, and it will be a big magnitude. And at the top, Because of the direct force P, it is compressive, and because of eccentricity T, it is tensile, and sum of these two will be this. So this is called the resultant diagram in pre-stressed concrete because of the pre-stressing force. Because of the pre-stressing force. Sometimes this may be with the stress diagram like this. At the top it may be 0, at the bottom it is a sum of these two values. Or otherwise sometimes depending upon the magnitudes, it may also be like this. A small magnitude of tension at the top and more value of the compressive stress. So resultant stress diagrams will be one of these two depending upon the magnitudes of direct stress due to direct force and also stress due to bending. So that means before the application of the loading, the entire bottom face is under compression and the top face is also a small amount of compression or zero stress, no compression, no tension, or sometimes maybe a small magnitude of the tension. So the important point here is after the application of the load, tensile stresses are going to induce at the bottom. So we need to provide initial compression at the bottom of the section. So that is possible by providing pre-stressing steel below the neutral axis. Below the neutral axis is shown in figure. So this pre-stressing steel, particularly for the case of simply supported beam, the pre-stressing steel must always be below the neutral axis only if the steel is of straight nature. And if it is of curved nature, depending upon the application and other forces acting, it can be changed. Types of pre-stressing. There are basically two different types of pre-stressing. Introducing the pre-stress to the concrete member, pre-tensioned pre-stressed concrete. Another one is post-tensioned pre-stressed concrete. So here, the tensile stresses induced in the member due to the application of the loads will be taken up by the initial compressive stress due to pre-stress, and the resulting stress on tension phase is very small. So that is the major concept that we are considering in the analysis and design of pre-stressed concrete. So there are two methods of introducing the compressive stress. One is pre-tensioned pre-stressed concrete, one other one post-tensioned. So here, as the name implies, that pre-tensioned means tensioning of the cable before casting of concrete, before casting the member. So pre-tensioning means tensioning the member prior to the casting of element. Post-tensioning means tensioning the pre-stressing steel after hardening of the concrete, after attaining the sufficient strength of the concrete. So tensioning is before the casting. Post-tensioned means tensioning the cable after attaining sufficient strength to the concrete. So these are the two different terminology. Now what do you mean by pre-tensioned concrete? Pre-tensioned pre-stressed concrete members are produced by tensioning the tendons or cables between the external anchorages before placing of the concrete. So first step is tensioning the cable and then placing of concrete. And after getting sufficient strength to the concrete, bond between steel and concrete increases as the concrete is getting hardening. When the concrete has reached the required strength, the jacking force is released and the force is transferred only by means of the bond from steel to the concrete. So initially the tensioned cable is by means of the jacks, That jacks will be there till the concrete gets hardened and attaining the sufficient strength of the concrete. And initially the entire tension is by means of the jacks provided at the ends of the cable. But after attaining the sufficient strength to the concrete, the bond, the transfer of the force or the stresses induced is by means of the bond between the steel and concrete. So here in pre-tension, the only the three steps. One is first pre-tensioning the cable by the jacking ends, then place the concrete, then see that the concrete attains required desired strength, and after that remove the jacks at either ends of the member. Whereas in case of post-tensioned pre-stressed concrete member, the tensioning will be done only after attaining sufficient strength to the concrete. So what you do, first cast the concrete member, leaving ducts for the cable, pre-stressed cable, and after attaining sufficient strength of the concrete, the tensioning the cables is done by means of jacking, and that is the way of introducing the pre-stress to the concrete. You can also see here the diagram. In case of pre-tensioned pre-stressed concrete, what we do is the first step is tensioning the cable, then casting of concrete or casting of element, and this is second step. Third step is removing the jacks after attaining sufficient strength. After attaining desired strength to the concrete. Desired strength to the concrete. That's all. So here, these are the only three steps. So here, in case of pre-tensioned pre-stressed concrete, the bond is the bond developed between these two as the concrete gets hardened. As the concrete gets hardened. So here, the minimum grade of concrete recommended as per IS 1343 is M40. For pre-tensioned concrete, it is M40. Similarly, post-tensioned pre-stressed concrete. So here, what we do first, fabricate the member, and leaving the ducts for the cables, And after attaining sufficient strength to the concrete, pass all these required cables through the duct and apply the tension by means of the jacking ends. Say this may be a jacking end and this may be say unjacking end. So here it is the cable is kept at, in proper position, whereas force is applied, tensile force is applied at the jacking end, so that the tensile force induced in the steel and compressive force induced in the concrete. Tensile force induced in the steel and compressive force induced in the concrete, the same magnitude. Here, the tensioning is done after attaining sufficient strength of the concrete. So the minimum grade of concrete here is M30. The minimum grade of concrete here is M35. Why the 35 here and 40 for pre-tensioned concrete? In case of post-tensioned concrete, by the time of tensioning the cable, concrete attains sufficient strength. So M35 is enough. Whereas in case of pre-tensioned pre-stressed concrete, the bond is going to develop between these two materials slowly as the concrete gets hardened. So that's why the higher grade of concrete is required for pre-tensioned pre-stressed concrete. Sometimes this may be a question. What is the minimum grade of concrete for pre-tensioned pre-stressed concrete? Or what is the minimum grade for post-tensioned pre-stressed concrete? So M40 and M35. Now here the two different types of materials are being used. One is high strength concrete. One is concrete, but that concrete is always a high with a high strength. You know that it is M35 means high strength. M40 means high strength. And minimum grade of concrete is M35 for post tension, 40 for pre-tension pre-stressed concrete. And another material used here is high tensile steel. Because here high strength concrete is being used, and at the same time large magnitude of the stresses induced in it, that is possible only when the steel is with the high tensile steel. Steel is high tensile steel. Mild steel and HYSD bars are not sufficient to transfer the stresses to the member, so that the large magnitude of the pre-stressing force introduced on the concrete. It is not possible with HYSD and also mild steel. Because of the high tensile stress in it, small quantity of area of steel reinforcement is required to give the desired pre-stress to the concrete. So always we go for high tensile steel, and it may be in the form of cables, strands, bundles, etc. And normally the cables are with the diameter 3 to 12 millimeters, and yield stress varies 800 to 1200 Newton per mm square. 800 to 1200 Newton per mm square. So high tensile steel. And it is high tensile, high tension, high tensile, high yield stress will occur because of the high carbon content. If the carbon content is more, then strength of the steel will be more. And at the same time, the ductility is less ductile. So you can see the graphs. It shows the maximum value. The stress is maximum. So you can look at here. The stress is maximum. Yield stress is maximum more, whereas the strain is very less. So when compared to the mild steel, it fails with a less deformation, less low strain. So high tensile steel fails at low strain. That means it is having low ductility. Ductility is very low. And maximum percentage of elongation for high tensile steel is around 10%. It's around 10%. So here high tensile steel and high strength concrete are required. High tensile steel and high strength of concrete are required for pre-stressed concrete. What are the advantages of pre-stressed concrete? Several advantages are there. That means the section remains uncracked. Whereas in RCC, the concrete area below the neutral axis is under tension, which is cracked. Whereas here, the entire section is uncracked under service loads. And because of that, reduction of the steel corrosion, durability increases, total concrete section is effective, moment of inertia is more, and thereby stiffness is also higher, and deformation is less, so that serviceability will be more, and shear capacity will also be more. Because sometimes it is also resists dynamic and also fatigue loading. Dynamic and also fatigue loading. Another one is a high span to depth ratio. High span to depth ratio. So because of high span to depth ratio, it is used for larger spans, particularly the bridges where the spans are very large, and sometimes in buildings where the large span beams are required, we can go for pre-stressed concrete beams. And if the span is same, less depth is required in pre-stressed concrete when compared to RC member, and because of that, self-weight is reduced, appearance also more, and aesthetic sense is more, economical also. And it is suitable for precast construction. So normally in RC members, most of the structures are constructed as cast in situ. Of course, nowadays we can also go for um, precast elements also. But in case of pre-stressed concrete, it is most suitable for precast construction also. By doing precast construction is very rapid. Better quality control can be achieved. Maintenance also less, and it can be constructed with the sort of repetitive members, and availability of the standard shapes also possible. Because of all these reasons, it is more advantageous than RCC. And limitations. Normally, there are certain limitations because high tensile steel and high strength concrete are required. It is normally costly when compared to other materials. And pre-stressing needs high skilled technology for introducing compressive forces on concrete by means of applying tensile force onto the steel reinforcement through jacks, and it needs a very high quality control and also inspection. These are the small limitations. And high strength concrete is required in pre-stressed concrete. Okay. Forms of pre-stressing steel. So several forms of pre-stress steel we used in pre-stressing members. Wires. Pre-stressing wire is a single unit made of steel. Then strands, two or three or up to seven wires are wound to form a pre-stressing strand. So if several wires are keeping together, that is called the strand. Tendon. A group of strands or group of wires are wound to form a pre-stressing tendon. Cable. A group of tendons form a pre-stressing cable. And bar means it is a relatively higher diameter, so that for lower diameter we call it as wire, and if the diameter of the bar is more, then it is called as a bar. Analysis of pre-stressed concrete members. Analysis of pre-stressed concrete members. Assume that take a simply supported beam having uniform cross-sectional area subjected to uniformly distributed load W per meter throughout. And here, because of the pre-stressing initially applying the force at this level, it is subjected to compressive force of P. Compressive force of P. The entire concrete is under compressive force of P at an eccentricity of E. So because of pre-stress with an eccentricity of E, direct stress due to pre-stress is P by A top and P by A bottom, which is positive, that is totally compressive. At any part of the section from left to right, the magnitude of it will be P by A positive. And because of the eccentricity E, Bending moment is P multiplied by E. Bending moment is P multiplied by E. So because of bending, bottom is under tension, bottom is under compression, top is under tension. You can look at minus. Minus indicates that top is under tension, bottom is under compression. This is nothing but M by Z. That is the section modulus ZB. ZB means section modulus about the bottom. Similarly, M by ZT, section modulus about the top. If it is a rectangular section, both ZB and also ZT are same, otherwise it is different. So these are the two magnitudes of the stress induced in the member by applying the pre-stressing force P. By applying the pre-stressing force P. So what is the pre-stressing force at the top? Because of the pre-stress, pre-stress induced at the top is P by A minus PE by Z. What is the pre-stress at the bottom? P by A plus PE by Z. So algebraic sum of these two is the resultant stress because of the pre-stress. And these are not at all formulas to be remembered. Everybody knows that direct force stress P by A, bending stress M by Z. So sum of these two is called the pre-stressing value. And because of the pre-stress, it may be the resultant diagram like this. Okay, the resultant diagram already I told you, it may be like this. It is only because of the pre-stress. So that means the entire structure is under compressive stress, or sometimes it may be with zero stress at the top, or it may be very small magnitude of tension and more compressive at the bottom. So this is called the resultant diagram by adding these two. So depending upon the direct stress, magnitude of direct stress and magnitude of the bending stress, this may be totally compressive. It may be the top of the section may be zero stress, or some part of the section is under, top section is under small tension. Okay, it is because of the bending pre-stress. Now, what are the types of loads acting on it? One is self-weight and another one is externally applied load. Now, mg means bending moment because of the gravity loads. Bending moment due to self-weight. mg, bending moment due to self-weight. You can calculate the magnitude of bending moment due to self-weight and divided by ZT. Similarly, mg by ZT. This is the bending stress because of the self-weight of the beam. And another one is externally applied load. If W is the externally applied load, moment due to loads, ML is the moment due to load, which is WL square by 8 in case of uniformly distributed load, or with any other loading, accordingly find out the magnitude of bending moment. And accordingly M by Z will be the bending stress. And you know that because of the bending, bottom is, and because of the externally applied load, bottom is under tension, top is under compression. So you can look at here, because of the dead load, bottom is tensile stress, and because of the loads also, bottom is under tensile stress. At the same time, top is compressive. Top is compressive. So now what are the total stresses that are there? Resultant stress. Resultant stress will be sum of the pre-stress and also the stresses developed because of the applied loads. So what is the stress at the top? P by A minus PE by Z plus mg by Z plus ml by Z. You can look at here. So these are the four different terms, and algebraic sum will be the resultant stress at the top. Similarly, For all these diagrams, the resultant stress means again algebraic sum P by A plus PE by Z minus mg by Z minus ml by Z is the resultant stress at the bottom. You can look at because of the pre-stress, the magnitude of the stress at the bottom is always positive, compressive. And because of the loading, whether it is self-weight or because of the externally applied load, the stresses are always under tensile. So it is positive, first two terms positive, second two terms negative. So for solving the problems in any of the competitive examination, 50% of the syllabus in precious concrete is basing on this only, this concept only. So no need of remembering any concept here. You know each and every formula and sum of all the stresses at the top, sum of all the stresses at bottom. Which stress is positive, which stress is negative, that needs to be understood. And what are the resultant stresses at the top or otherwise at the bottom? Because of the pre-stress it is compressive and because of the loads it is negative. So what is going to happen? The resultant stress may be with a small magnitude of compressive stress or resultant stress may be zero at the bottom or resultant stress may be with a small magnitude of the tensile stress. If it is small magnitude of tensile stress and it is well within the limit of the tensile strength of the concrete, then there may not be any problem. Okay, so these are the stress diagrams. And what is the resultant stress at the top? At the top, because only moment due to pre-stressing force creating the tension, and all the remaining three terms are contributing the compressive stress. So more compressive stress at the top, more compressive stress at the top. So here, before the application of the loading, the important thing is see what is the sigma t at the top, because whether the tensile stress is zero, having some positive value, compressive value, or negative value, because there is a possibility of developing the negative value here. So that's why sigma top because of the pre-stress is important. And after the application of the load, there is a possibility of occurring tensile stress at the bottom. So here we require for observation of sigma b. The stress induced at the bottom will be what? Similarly, stress induced at the top because of the pre-stress is what? So sometimes the majority of the questions will be because of the pre-stress, if sigma t is equal to 0, what is the magnitude of pre-stressing force or what is the magnitude of eccentricity? That may be the question. Because of only the pre-stress, there is a possibility of top stress at the top of the beam equal to 0, and accordingly you can find out the unknown. The other one is because of the pre-stress and also the application of the loads, the soffit of the beam, soffit means bottom of the beam may be subjected to tensile stress or zero stress. Sometimes the condition may be if the stress at the bottom is equal to 0, then what is the magnitude of P or what is the magnitude of E or whatever the magnitude of any other unknown parameter can be the question. So ultimately, these four magnitudes of the stresses are more important, and this diagram is more important. You need to keep this diagram always in mind, not by means of by hearting the formulas. And of course, it is only the previous one. It is a stress at the top of the section, sum of all the algebraic sum of all terms. Similarly, stress at the bottom, it is also algebraic sum of all. It is just discussed clearly. The questions in the examination may be, what is the stress due to pre-stress at the top at bottom? Because of the pre-stress only, at the top is sigma t. Because of the pre-stress only at the bottom, these are the two values, two equations. And sometimes resultant stress due to pre-stress and also loading. Pre-stress and also loading. All the four terms will come into picture. Sometimes what is going to happen, the dead load and the live load may be only one. Sometimes in the question, both dead load and live load will be like uniformly distributed load. So what you do, this will be combined together. Simply you can write M by ZT. M by ZT. Because normally dead load is very small when compared to the load acting on the structure, and sometimes that may also be added to the W load, so that you can use only one term. If it is given separate, go for two different terms. Otherwise, only one term is enough. And this is the most probable question. Already I told you, bottom equal to 0 means, P. This is because of the pre-stress, because of the externally applied load moment, and you can find out P. Or sometimes the question may be, what is the magnitude of E? So nothing to worry, just observe the type of equations required, that is enough. And for rectangular beam section, Z is BD square by 6. Normally what is Z value? Z is equal to I divided by Y. In case of rectangular section, Z equal to Z bottom and also Z top, all are one and the same. But in case of any unsymmetrical I sections like this, any unsymmetrical sections like this, if the moment of inertia and also position of neutral axis, everything is given, you can compute. But for computing moment of inertia itself may not be the question, because it will take a lot of time. If the questions are like this, so what they will provide you, the moment of inertia will be given, the y value to the top is given, y to the bottom is given, everything will be given, only you need to calculate ZB and also ZT. So ZB and ZT are different for the unsymmetrical sections. Whereas for rectangular section, it is symmetrical, BD square by 6. And this entire thing is not required. You need not remember all these things. It's only one form of deduction. So what is that? P by A, that is written here. P by Z, ZB. So what is ZB? I by Y. So I multiplied by D by 2. I divided by D by 2. I by Y will be equal to M by Z, means again M by I into D by 2. So again you can write this P by A, P by I means AK square. K is the radius of gyration. AK square, K is the radius of gyration. I can be written as AK square, and here also I can be written as AK square. In the first two terms, P is common. You can take P out, 1 plus ED by 2K square, and you can write this. So this may be the equation for computing P or computing E. But don't try to remember this equation. It's not required at all. If you don't know this one, you can find out directly the P value or E value or whatever may be the unknown value. So, okay, so don't try to remember like this. So if the stress at the bottom is 0 and P is given, magnitude of the pre-stressing force is given, you can find out the eccentricity. If the eccentricity is fixed, how much magnitude of the pre-stressing force, that can be found from the original equation. This is the original equation. Without any thing, you can easily remember the equation. Next, sometimes already I told you, because of the pre-stress, the stress at the top may be 0. So stress at the top may be 0. So what is the stress at the top? P by A minus PE by ZT. P by A minus PE by ZT means I AK square and divided by D by 2. So accordingly, you can take P by A from these two out, 1 by 1 minus this, it is equal to 0. So that what is going to happen? 1 minus ED by 2K square equal to 0. So from this you can write ED will be equal to 2K square. Don't remember this also. Not required. Don't remember. It is obtained from the original equation that everybody knows. But sometimes in the examination, if K is the radius of gyration, D is the depth of the beam, E is the eccentricity, these three are related as. That may be a theoretical question, very rarely, occasionally, such a things may occur, may come into examination. In such case, you always deduct such a type of small equations from the original equations. If you try to remember now, it may not be long lasting. You will forget in within few days. So don't try to depend on such a type of equations. You always depend on your mind only with the basic equations. Now, pressure line or thrust line. Pressure line or thrust line. So what is going to happen here? Because of the compressive force induced through the pre-stressing cable, the entire structure member is under compression. So because of the compression, the thrust will produce. Because when the member is under compression, the thrust will produce, and thrust is having a different magnitude and different, it will also acting at a different position depending upon the magnitude and also the eccentricity of the pre-stressing cable. So here the pressure line is the locus of the points of application of the resultant stress at different sections along the length of the member. For example, here at midspan, you know how to calculate the stresses. Stress at the top is P by A minus PE by Z plus M by Z. Similarly, stress at the bottom is this. So because at the center, bending moment is more, so the third term is more, you will get the small magnitude of the stress at the bottom and the maximum magnitude at the top. And resultant of this trapezium will lie at this point, red mark. That is the point of application of this resultant. That is called the point of application of the resultant. That arrow mark shows the resultant of the stresses at that point. That will be same as this. This is the point. This is the point. You can look at here. It's not. This is the point. So this point is corresponding to resultant of this diagram. Resultant of this stress diagram at the center. Similarly, if we consider at some other point, say L by 4, at L by 4, okay, this is at midspan, at L by 4, what is going to happen, you know, at the stress at bottom, stress at the top, and resultant will be at this point. So this arrow mark is a bit closer to the neutral axis. And this is the stress diagram at the end. So at the end, what is the bending moment? Bending moment is 0. So that means the third term is going to become 0, and this is the resultant stress diagram. It will be acting exactly at the point where the cable starts. So that means this is one point, it is another point, one more point, and if you put another section here, it is another point. So like that. So that means the pressure line or thrust line is locus of the resultant of the stress diagram at different sections along the length of the member, So this is called the pressure line, or otherwise you can call it as thrust line. So sometimes finding the position of thrust line is also not difficult. You can easily find out the position of it. Now, pressure line or thrust line for a member subjected to concentrated load. In the previous diagram, you can look at here. Since it is concentrated load, since it is uniformly distributed load, the bending moment diagram is parabola. And bending moment M value varies with parabolically. M varies parabolically. Accordingly, the introduction of this M value parabolic, so the stress also varies parabolically, and the resultant thrust is follows parabolic shape. So that means here the shape of the external bending moment due to external load is same as the shape of the thrust diagram or pressure line diagram. And this is another one. Pressure or thrust line diagram when a member is subjected to concentrated load. If a concentrated load is subjected and the cable is as usual at the bottom, and compressive force is applied at the bottom at the point of contact with the cable, and the thrust diagram is a triangle. So in the similar way, if you find out the resultant of the stresses at any point, this is called the locus of the resultant of all the points along the length of the member. So the shape of the thrust diagram is same as the shape of the bending moment diagram due to externally applied load. Okay, so the locus of the application of the, this is the same. Now, the shape of the thrust line is same as that of the shape of the bending moment diagram due to load. Already we had some discussion. Now, how much it is shifting? You can look at here. This is the height shifted. Originally, the cable is at this level, and the thrust position is shifted to certain level. So that can be computed here. You can find out here at this level how much is the shift. This is A. So at any point we can find out how much amount of shifting of the position of the thrust from the cable. So for that A will be equal to M into P. Shift of the pressure line from the cable is M is equal to A into P. It is not a new formula. Don't think that nothing is there in it. No formula at all. What is the moment at this point? You can look at what is the moment at the tip of the point. The moment at that point will be equal to, because of P multiplied by A. What is A? A is the distance of the thrust point from the cable. Distance of the thrust point from the cable is small a. So M is equal to P into A, and accordingly the shift will be equal to M by P. Don't remember anything. What is this M? M is the bending moment at that point. What is that bending moment here? Now M will be equal to WL by 4. And if you want shift at some other point, say A1, what is the relation? M1 is equal to P multiplied by A1. What is M1? Moment at this point. Moment at this point is M1. And P is anyway constant, that is pre-stressing force acting on the cable. And A1 is the shift corresponding to the position of moment M1. So like that you can find out any position, any place, what is the distance of its thrust line. What is the distance of its thrust line from the pre-stressing steel reinforcement. Okay. So don't treat that all these are the formulas. Since it is at the middle, normally we require WL by 4, A is equal to this, and you will get it. Don't remember anything here. You always try to understand the basic concept. From that, you can answer any type of questions without remembering any formula. It is not at all a formula. Next one, load balancing concept. Load balancing concept. So remember here the meaning load balancing. What is that it is going to balance? Already introduced pre-stress in the member. Already introduced pre-stress in the member will gets balanced. Will gets balanced with the same with the effect of the load. With the effect of the load. So that means apply the pre-stressing force with a certain eccentricity such that the entire pre-stressing will be nullified because of the load acting on the structure. Load acting on the structure. That is called the load balancing concept. Already compressive stress induced in the structure. That entire compressive stress induced in the structure will get nullified by the application of the externally applied load on the structure. This is a simple concept. Load balancing concept. The selection of a cable profile in a pre-stressed concrete is in such a way that the transverse component of cable forces balancing the given type of external loading. For example, at the end, what is the bending moment at the end? For example, at this section, at this point, say you can call some D. What is the magnitude of the stress at D at this level or at the bottom? You can call dB. That means stress at the bottom at the point D. So what is the value? You know that it is P by A. You know that it is P by A minus PE by ZB and plus PE by Z minus M by what is the value? Minus M by Z. So in this particular case, you can look at the end, is there any balancing concept? Because of W, what is the bending moment at the end? Bending moment at the end is 0, so this term vanishes. When this term vanishes, why do you apply more compressive stress? Why do you apply more compressive stress? So that's why putting here E is 0. When E is 0 means this term also vanishes. That means since here there is no balancing of the stresses, there is no balancing of the stresses. So that's why when there is no bending moment, we are also keeping eccentricity also 0. So that only P by A will exist. Only P by A will exist. And similarly at the center, where the bending moment is more, that entire bending moment will be balanced by the pre-stressing force. Balanced by the pre-stressing force. So here what we do is, here the shape of the cable is more important. The selection of the cable is more important. It is clearly given that the selection of the cable is such that it produces the same as that of external load. Because of the load, bending moment is more at the center, so eccentricity will be more. And due to external load, bending moment at the end is 0, the eccentricity also 0. That means at every part of the section, the load gets balanced by means of the pre-stressing force induced in the cable. So that's why maximum movement due to cable. Sometimes questions are for load balancing concept. What is eccentricity? The question may be, what is eccentricity? I will tell you a little later. So here in the case of load balancing concept, Because of the pre-stressing force, what is the moment induced here? Moment induced is P multiplied by E. You can look at P into E is the moment induced. What is the moment because of the external load? That is WL by 4. It is not at all a formula. Everybody knows that P into E is the moment, WL by 4 is for concentrated load. That's all. Sometimes in the examination, the one of the option may be this. One of the option may be this. So don't by heart these formulas, not required. Don't by heart. But because of the concept, P into E equal to WL by 4, that you know. That's all about it. From this, if all parameters are known, you can find out what is E. If all parameters are known, find out what is W. If all parameters are known, how much load it can support so that it gets balanced. So using only this particular formula equation, you can find out the various unknown parameters. Sometimes a theoretical question may be asked in the exam. What is the E value? WL by 4P. Don't remember anything. This is the equation that you need to develop. That is for the case of concentrated load. Because already I told you, the shape of the cable depends on the shape of the bending moment diagram. So here the load is uniformly distributed load. When the load is uniformly distributed load, what is the shape of the bending moment diagram? Shape of the bending moment diagram is parabola. Since the shape of the bending moment diagram is parabola, what is the shape of the cable? Cable also parabola shape. Cable also parabola shape. Then load balancing is possible. So here also, because what is the maximum moment here? P multiplied by eccentricity, PE. What is the bending moment because of uniformly distributed load W per meter, WL square by 8. That's all. So these bottom equations are coming obtained from the top. So from this you may get what is E, what is P, and what is uniformly distributed load, etc. Any unknown parameter can be found using the equation. So if you try to by heart all these, it's very difficult to recollect the same in the exam. But it is very easy for anybody to understand the equation and develop the equation. The third possible case, normal cases, or one-third concentrated loads. So W concentrated loads are applied at one-third points. So L by 3, L by 3 and also L by 3. If it is at L by 3 distance and two concentrated loads are reacting, you know the reaction is W. And what is the maximum bending moment? Maximum bending moment will be W into this distance. What is that distance? L by 3. W L by 3. What is the shape of the bending moment diagram for it? The shape of the bending moment diagram for this will be like this. So the maximum bending moment is uniform between the loads and thereafter it is decreasing. So this is called the shape of the bending moment diagram. So the shape of the cable also in the same fashion with zero eccentricity at the supports and E uniform eccentricity between the two loads. Accordingly, what is the maximum bending moment because of P? So it is P into E. That you know. What is the bending moment WL by 3? That also you know. That's all. This is the only equation that you can be able to formulate. Like that, this is the load balancing concept. In the load balancing concept, whatever the loads that are acting externally on the structure will get balanced by the pre-stressing force itself. Okay. Sometimes the question may be a little bit different sometimes depending upon the loads. So sometimes not only that, if the concentrated loads are acting at L by 4. For example, this is L by 4 distance. It is L by 4 distance, L by 2 distance. Two concentrated loads are W. So the reactions are W. What is the maximum bending moment? Maximum bending moment will be equal to W into L by 4. W into L by 4. So you should calculate this because it's a very primary thing. And how the cables are provided here? The cables are provided. This is the neutral axis. This is the neutral axis. How the cables are provided? It should be provided only like this. So with the constant, from this point to this point, the eccentricity is uniform, and beyond that, it will be joined to the original. It is P and P, the compressive force P. So here, what is the equation similar to that? P into E will be equal to WL divided by 4. And from this equation, you can compute any of the unknown parameter in the examination. So this is how the load balancing concept in pre-stressed concrete. Okay. Now with this, the analysis is over. So in total, the load balancing concept, small equations that you can be able to understand. And another point is the computation of the stresses at the top and bottom of the sections. So this is at the top and this is at the bottom. So sometimes if the pre-stressing cable, if the pre-stressing force through the cable is exactly at the neutral axis, In previous, that means this is the cable. The cable is provided exactly at the neutral axis. When the cable is exactly at the neutral axis, what is eccentricity? Zero, no eccentricity at all. When there is no eccentricity, what is the stress at the top? Stress at the top will be P by A, stress at the bottom also P by A. And P by Z term is vanished because eccentricity is zero. We can call it as concentric cable. Concentric cable. That means cable is provided concentrically passing through the neutral axis. So second term is neglected. And whatever the third term, it is nothing but M by Z, ZT, and here minus M divided by ZT. So this is the equation when the cable is located at the center neutral axis, passing through the longitudinal neutral axis. Okay, so like that, these are the only. These two are the only equations. And if you understood this concept, you can answer any type of questions in this pre-stressed concrete structural analysis. Okay. Now another important topic is losses of pre-stress. Losses of pre-stress. There are two different methods of introducing the pre-stress in the members. One is pre-tensioned, already you know. The various losses in pre-tensioned pre-stressed concrete are loss due to elastic deformation of concrete, loss due to relaxation, loss due to shrinkage, loss due to creep. Sometimes the question may be, which of the following is not a loss in pre-tensioned pre-stressed concrete? A, B, C, D. Out of this, only three of these will present and fourth one is some other thing. So you need to remember only four losses are there in pre-tensioned pre-stressed concrete. Whereas in post-tensioned concrete, six losses are there in total. What are the six? Five because of the friction. The loss due to friction? Because the cable is tensioned after attaining sufficient strength of the concrete. So there is a frictional resistance while applying tension to the cable. So there is a loss due to friction. And another one is loss due to anchorage slip. Anchorage slip means after attaining a sufficient tension to the cable, and the cable is going to be removed after completion of the work. At the time of removal, there is a slip that is called the anchorage slip. So these two losses exist only in post-tensioned pre-stressed concrete. Post-tensioned pre-stressed concrete. Remaining four losses are there in both, but in case of loss due to elastic deformation of concrete, if all wires are tensioned simultaneously, no loss. That means if the cable, if the structure is having, member is having several cables here and all the cables are tensioned at a time, then there is no loss due to elastic deformation. If all cables are tensioned at a time, I will explain little later. Yeah, I will explain in detail. If the wires are tensioned one after the other, one wire is tensioned now, after completion of first wire, then tensioning the second wire, and completion of first two, then tensioning of the third one. Like that, if we proceed, then there is a loss of stress due to elastic deformation in post tension. Otherwise, if all the cables are tensioned at a time, no loss, and the remaining losses also will be there in it. So it is most important which type of losses occur in pre-tension and also post-tensioned concrete. And these are the some of the small equations that you need to remember. Loss due to elastic deformation of concrete, and it is for pre-tensioned pre-stressed concrete, because in pre-tensioned concrete there is a loss, post-tensioned there is no loss, and there is a possibility of loss. So that's why we are here separating this for calculation of values for pre-tensioned pre-stressed concrete. For pre-tensioned pre-stressed concrete, loss due to elastic deformation is alpha multiplied by Fc. Alpha is modular ratio, that is ES by EC, modulus of velocity of steel by concrete, and normally these are the values that will be given in the exam. And FC means pre-stress in concrete at the level of pre-stressing steel. Pre-stress in concrete at the level of pre-stressing steel. That means here you can look at what is the magnitude of the stress. You can look at here, at this point, what is the magnitude of the stress at a particular given point. So the stress at this level is so okay, remember it. FC means pre-stress in concrete at the level of pre-stressing a cable. At the level of pre-stressing cable. Say for example, if you want to calculate the stress at this here across this section, what you do at this point, the stress in concrete is FC. What is that value FC? How to calculate FC value is now more important. So here the different types of cables are possible for straight cable. If the cable is straight, uniform pre-stress throughout the cable. There is no change of stress, uniform pre-stress will occur, and this will be FC equal to P by A, first term, P by A, throughout the length of the cable. M by I into Y. Actually, this is M by Z. Z will be used only for either bottom or for the top. But here you want to find out the stress at the level of the steel reinforcement, at the level of pre-stressing steel. stress at the level of pre-stressing steel. So M by I multiplied by Y. What is Y value here? Y value itself is E only, because that Y is the distance of the pre-stressing cable from the neutral axis. So here E and Y both are one and the same in case of straight cable. Then for parabolic cable can be one of these ways. Parabolic cable can be provided with eccentricity E at the center and zero eccentricity at one end, zero eccentricity at another end. This may be the parabolic cable. And sometimes what we do is parabolic cable can be provided with E at one end, at middle, E1 at one end, and E1 another end. E1 are the eccentricities at the ends, and eccentricity at the middle is E. Sometimes the cable may be parabolic. It may start above the neutral axis, so that here we call it E, and say this is E1 and this is E1. That means it is on the other side. It is on the other side. So if the cable is parabolic in nature, what we do is we compute the value of the stresses at different points. Compute the value of F1, compute the value of F2. Because here eccentricity is varying, Y is also varying. So the stress from one end to the other end is varying. So we have to consider the average value as the FC value. Average value. In the previous case, already I made some statement. You can look at here. Uniform pre-stress occurs throughout the length of the cable. Uniform stress occurs. So that's why we are using FC. Whereas in this case, F is different at end, is different at the middle. So you call F1, F2 are the stresses at the end and middle, and accordingly compute it. And FC will be average value. Here average means the variation is parabolic. So F1 plus 2/3 of F2 minus F1 is the average value. FC can be taken in that way. FC equal to stress at the end plus 2/3 of the difference. That is the FC value. Once this FC value is known, then for computing loss of pre-stress is alpha multiplied by FC. Then for post-tension concrete, the important thing is if all wires are tensioned at a time, no loss. Sometimes question may be very big, and in that this line is given. If all wires are tensioned simultaneously, the magnitude of loss of pre-stress due to elastic deformation is, answer is 0. And if you want, you can calculate with so many values that also appear in the as one of the option, but the question is, the answer is no loss. If all wires are tensioned at a time simultaneously, no loss. And another case is if wires are tensioned one after the other, first cable tensioned, then second tensioned, third tensioned, fourth one, like that. If you tension the cables one after the other, then there will be a loss in the previous wire. For example, here you can imagine that this is a box, cartoon box, and in this direction it is tied first. So that means tension is applied in this cable. Afterwards, if you apply the tension in the other direction, to keep perfect, what is going to happen? There will be some loss in previous cable. It gets relaxed. The stress will be less. So in the same way, When cable 1 is tensioned, there is no loss because the first is cable itself. When cable 2 is tensioned, the loss is in cable 1. Cable 3 is tensioned, loss in both cable 1 and 2. Cable 4 is tensioned, loss in 1, 2 and 3. So you can imagine that one side if you put a rope for a box, it gets tightened. And if you keep the same type of rope on the other side and again tightening on the other side will definitely release the stress in the first one. First one. So like that it will be the same case. Second one is loss of stress due to relaxation of stress in steel. That means doing so, that means once the tension is applied, and by the time when you finish, there will be some relaxation. Even while putting a knot to a cotton box, while putting a knot to the cotton box, initially at the time of putting knot, it is completely tensioned. Just after completion of the knot, some part of the stress is relaxed. That is called the relaxation of the stress, which is around 5% of the initial pre-stress. In the examination, if it is given some numerical value or some percentage, you can compute accordingly the magnitude. Then loss due to shrinkage of concrete. Sometimes concrete gets shrinks, and because of the shrinkage, the stresses induced in it, the stresses loss of pre-stress will be shrinkage strain, ECS, shrinkage strain multiplied by modulus of elasticity, of steel. So what is ECS, shrinkage strain? As per the code it is given, this is only code values. 300 into 10 power minus 6 is the strain in case of pre-tensioned pre-stressed concrete member. And 200 into 10 power 6 by log E T plus 2, it is for post-tensioned pre-stressed concrete. And here T depends on the age of concrete in days. So anyway, remember this value, that is point about 0003. Point 0003 is the shrinkage strain in concrete, whether it is RCC or pre-stress or anything. Point 0003. And for post tension, this is the equation. So once you know the numerical value of the strain, by multiplying the modulus of elasticity, that will be the loss. It's not computation required. In the question, if it is given shrinkage strain, and also modulus of velocity, it's only multiplication of it. That's all. Normally the symbol is psi CS multiplied by ES. Okay, no problem. So it is only the strain, either you can use small e or psi, both are one and the same. Then loss due to creep of concrete. The same procedure as that of the loss due to elastic deformation of concrete. Loss is here. Already you know that using deformation of the concrete alpha into FC. It is loss of stress due to elastic deformation. Now we are multiplying the same by phi value, it is creep coefficient. So already you know how to calculate FC, how to calculate alpha. Now for a given value of creep coefficient, you can find out the loss of pre-stress due to creep of concrete. So here computing FC is tedious. Otherwise second loss is okay. Loss due to shrinkage is alright, loss due to creep of concrete. All these losses can be found with by knowing this simple formula. So remember this small formula here, it is required to know. And in the examination, the creep coefficient will be given according to the age of concrete and used appropriately. Next, loss due to pre-stress due to friction. This is in only post-tensioned. This is only in post-tensioned pre-stressed concrete member. It is not there in pre-tensioned. It is only post-tension. What normally we do is, this is a structural member. It's a structural member. This structural member is casted, leaving the duct throughout, leaving the shape of the duct throughout. At the time of casting itself, some pipes will be kept in this particular direction. When pipes are kept in this direction, it will be it will form a clear cut duct. And after attaining sufficient strength to the concrete, insert the cable from one end to the other end. Insert the cable from one end to the other end, and keep tightened at this point. So keep the bar without any movement at this point. And the other end, the cable is passing through the jack. This is called the jack, and you can call it as jacking end. It is called jacking end. So by jacking end with the by means of the jacks, the tension is applied onto the cable. Tension is applied onto the cable. So while applying the tension to the cable, what is going to happen? This cable is very close in contact with the surrounding concrete. And there is a moment of the there is a moment, small moment, because the increment of the length is possible. So because of that, frictional resistance will induce. And also, the concrete may not be perfectly smooth and small waves may be there, and because of the waves, wave effect also will be taken into consideration. And accordingly, the code has given the relation between the pre-stressing force at the jacking end and at any other point. So you can remember, look at here, P naught means initial pre-stressing force or pre-stressing force at the jacking end. And at any distance, say x, the force in the cable is nothing but px. Force in the pre-stressing cable is px. So px and p naught are related by this equation. Px equal to p naught into e power minus mu x plus kx. And this is simplified, and this will be the final equation. So P naught Px equal to P naught into, you can see that one, 1 minus mu alpha plus Kx. And what is the loss of pre-stressing force? Loss means P naught minus Px. Original minus the value is the loss. So from this equation, the loss of pre-stressing force is P naught into mu alpha plus Kx. So this is the important formula to be remembered. So loss of pre-stressing force will be equal to P naught into mu alpha plus Kx. And what is the loss of pre-stress? It is force. Stress means divided by area. So here force by area, it is pre-stress. Similarly, P naught by area is nothing but F naught. F naught means initial pre-stress. F naught means initial pre-stress. So the question may be in terms of the pre-stress, loss of pre-stress, or in terms of the loss of pre-stressing force. So this is the only equation you need to remember. But here, what are the various values? P naught means initial pre-stressing force. Px means at any point the force in the pre-stressing cable. Mu means coefficient of friction between the cable and the duct concrete. Alpha is the cumulative angle of the both the ends of the cable. That I will tell you clearly. Cumulative angle. If you draw the tangent here and draw the tangent here, the angle between these two is called the cumulative angle, or simply change in the angle from jacking end to the unjacking end is alpha. K is the coefficient which is considered for the wave effect, and that is 0.015 per meter. X is the distance from the jacking end. So keep this figure in your mind, not only the formula. If you just remember only the formula, sometimes the question may be a little bit twisting and you may not be able to answer the question. But the formula along with this diagram, if you keep in your mind, it's very easy to answer any type of questions. Now here these are the various values that are given. Normally coefficient of friction is 0.25 to 0.5, and it may be even sometimes more. Coefficient of friction for wave effect is 0.015 per meter. That means for 1 meter this is the value. But in the new examination, if there is a numerical question, all these parameters are given. If not, you should be able to assume it. Alpha is cumulative angle of radiance through the tangent to the cable profile drawn between any 2 points under consideration. So normally loss of pre-stress means at the jacking end to the unjacking end. This is only at the point where x distance. But what is the total loss? Total loss will occur from the jacking end to the unjacking end. So at this point, if it is P0, here it is some other value P1. P1 is always smaller than the P0 value. So this is the only equation that you need to remember for solving any problem on friction, loss due to friction. Now, here everything is known in the equation, alpha, mu, it will be given in the exam. K also given in the exam. X means from one end to the other end, that is a span. That is also given. And P naught, initial pre-stressing force, that is also given. What is the unknown value? Alpha. So here, computation of alpha is more important. If you understood how to calculate alpha, this computation of the loss is very simple. Because all other parameters known, even here F naught is known, mu given in the exam, K also given, X is also given, it is length of the beam or member. Alpha is the only parameter you need to calculate. Now, alpha value for a straight cable. This is a straight cable. What is the alpha value from one end to the other end? Alpha means angle between the tangents drawn to the cable at the ends. So here alpha value is 0 because at this end, that end, there is no change in the angle. So alpha value equal to 0. If the question is a straight cable, then the numerical solution is very simple. Mu alpha first term is 0, only effect is because of the wave. Okay. And another one is, sometimes the cable may be of triangular shape. If the cable is of triangular shape and it is a height h or eccentricity e, whatever it may be. And what is alpha? Alpha is, if you draw the tangent, this is a horizontal line. It is inclined line. And at the another point, if you draw the line, so this is called the alpha value. This is called alpha. Alpha is the cumulative angle between the tangents drawn from the two ends. So this is one tangent and this is another tangent, it is alpha. Once it is alpha, this angle is alpha by 2, it is alpha by 2. And this angle is very small, so tan theta will be equal to theta. So tan theta equal to, that means tan theta alpha by 2 equal to, what is height? H divided by, what is the horizontal distance? H by 2. So don't treat it as a formula. Don't treat it as a formula. So it is nothing but tan theta, which is equal to theta, that is alpha by 2, opposite side divided by adjacent side, and this is the equation that you can develop at any point of time. So don't by heart this. Then for parabolic cable, sometimes cable may be parabolic in nature. If the cable is parabolic, you know the equation of parabola, 4 yc by yc means the cable, dip of the cable, or h, 4h by L square x into L minus x. Okay, and for this, if the tangent is drawn at this point means the slope. What is the slope at that point? So slope means dy by dx equal to, you differentiate this, it is 4h by L square L minus 2x. This is the slope equation. Once the slope is known, what is the what is the alpha value? You can look at here. This can be known. And at x is equal to 0, at the jacking end, x is equal to 0 means jacking end. What is dy by dx here? Put here 0. Or what is the value? When it is alpha here, this is alpha by 2. Okay, when it is alpha, here it is alpha by 2, and this is also alpha by 2. So dy by dx equal to alpha by 2. And at the same time, put here 0. 4h by L square L minus 0. What is that you will get? You can see 4h by L square L minus 2x means 0. So from this, alpha equal to 8h by L. Don't by heart this. Don't by heart this. If it is a question in the examination, put your mind, keep your mind for analysis. Otherwise, not required for this. Okay. So everybody knows that equation of parabola, because already arches and other related topics in analysis is over, and you know the equation of the parabola. So accordingly, if I can find out alpha value. Next, if it is a circular cable, how to calculate alpha? You know that this is a beam and the cable follows a circle. Assume that it is circle. It not looks like circle. It's a circle. You know that it is. It follows the complete circle. So in this particular case, there are two ways to define this. One is sin alpha by 2. You know here, if you join the ends with the O, this is alpha by 2, and this is again alpha by 2, and this is again alpha by 2. Okay, if this tangent is alpha by 2, this is alpha by 2, that is alpha by 2. It is also alpha by 2 here. So sin alpha by 2 is, what is this opposite side? Opposite side is AC. AC means L by 2. What is the hypotenuse? Radius. That's all. If you just, and what is alpha by 2? Sin alpha by 2 is nothing but alpha by 2, and this is the equation. So you can derive these equations at any time in the examination if it is a question in the exam. But don't try to remember. If you try to remember, you do not know what is alpha, L by R, L by 2R, L by 4R, L by 8R. It is always under confusion. And for a given this, how to calculate the radius of circle? For radius of circle, you know, by rule of chord, AC multiplied by CB, you see, AC multiplied by CB equal to this vertical distance. What is the distance? This is CD. You call this point D. CD multiplied by CE. CD multiplied by CE. What is AC and CB? It is L by 2 because half of the span. And what is this value? It is nothing but cable height h. And what is the remaining? 2R minus h. So here h square, h is very small, and neglect that. Accordingly, radius of curvature equal to L square by 8h. So this is how for a different shape of the cables for computing the alpha value. Once you know the alpha value, it's very easy to calculate the loss due to friction. Loss due to friction is F naught mu alpha plus Kx. So always remember anything if necessary along with the diagram. Then only you can answer the questions in the gate examination. Otherwise, though you know formula, everything, the question sometimes may be a little bit in a twisting mode and you may not answer though everything is known to you. The last one is loss due to anchorage slip. Loss due to anchorage slip. So what is anchorage slip here? The because of the jacks, because of the jacking arrangement, the cable is gets tensioned to the desired level. And at the time of removing the jack, there will be some relaxation in the cable, relaxation of the stress in the table. That relaxation will be, it is going to relax, the entire cable is going to relax by amount of delta. That is called the anchorage slip. It is going to slip by delta. And you know, everybody knows that delta is equal to PL by AE. And from this, what is P by A? P by A equal to delta E by L. P by A is stress. P by A is stress. So what is that you are going to calculate for the slip of delta? For the slip of delta, what is the corresponding stress? When there is a slip, the corresponding sigma is called the loss of stress, and this is the formula. Don't by heart this also. Don't by heart this also, because everybody knows about this delta equal to PL by AE. From that you can develop the equation at any stage. So that's all about the complete theory in pre-stressed concrete. So with this entire theory, if you read the material once, twice, thrice, then you can answer any type of question in the examination. So let us go for some numerical questions in pre-stressed concrete. A rectangular, simply supported beam of span 8 meters and size 200 by 400 meters is pre-stressed by a straight cable carrying an effective pre-stressing force of 600 kilonewtons located at an eccentricity of 100 millimeters. 100 millimeters. So here P is also given 600 kilonewtons. Size of the section is given, which is equal to 200 by 400 overall, and pre-stressing cable is at this level, and it is called the eccentricity. Okay. The beam is subjected to uniformly distributed load of 15 kilonewton per meter, inclusive of self weight. Here, inclusive of self weight. So, moment term, only one term will come into picture. The question is, the stress induced at the top and bottom fibers of midspan respectively are. So, what is the question? At midspan, what is the stress at top? What is the stress at bottom? This is the question asked. And you know the original procedure, you just go through it. But what you know, what are the terms? You need to find out P by A, you need to find out P by Z, and also M by Z. So for this, what are requirements? Area. So calculate this area. Calculate the area. And then eccentricity is known, that is to be found. That is BD square by 6 and it is known. Eccentricity is also given. And in this term M, if for M is WL square by 8, that also known. And substitute get P by A, PE by Z, M by Z, and these are the three values. What is the resultant stress at the top? At the top, P by A minus and plus. Plus, minus, plus. You should imagine along with the diagrams. So substitute the value 10, 15 and this, and it is the top stress. Since it is positive, the nature is compressive in nature. And resultant stress at bottom, these two are positive and it is negative, you will get 2.5. It is also still a positive value compressive stress. That's all about the question. Sometimes the question may be, if the stress at the soffit of the midspan, soffit means bottom of the midspan is equal to 0. What is the condition given here? Sigma bottom equal to 0. The magnitude of the pre-stressing force required is, what is the magnitude of P? Eccentricity is same. So what you do, sigma B means P by A, P by Z minus M by Z equal to 0. So accordingly, substitute various values and you will get P equal to 666.7 kilonewtons. So understanding this equation is important. Substitution of the values in that is not a big thing, and of course for computation of these value within stipulated time is also more important. So you need to work with the calculator. Then only you should know how to get the value within possible minimum time. Next question. A simply supported pre-stressed concrete beam 9 meters of size 200 by 400 mm is subjected to two concentrated loads of 50 kilonewtons acting at 1/3 points. The cable has an eccentricity of 100 mm between the concentrated loads. You can look at 100 mm between the concentrated loads and reduce linearly to 0 at the supports. If the self weight of the beam is neglected, the magnitude of the pre-stressing force in the cable for the load balancing is, the load balancing concept. What is the load balancing concept? It is 3-3-3. The loads are acting at 1/3 points. So what is the bending moment? Bending moment is WL by 3. What is the moment due to pre-stressing force? P multiplied by eccentricity E. So that is P into E. Substitute the values and that is the answer. Sometimes you can look at question may be very big. The answer is very simple by understanding this equation, understanding this relation. Okay, that's all about the problem. Next question. A pre-stressed concrete rectangular beam of effective span 8 meters and 200 by 400 mm is pre-stressed by means of high tensile wires of area 500 mm square. Located at 80 mm from the soffit of the beam. So here it is given that it is 200 by 400 millimeters and it is located at a distance of 80 millimeters from the soffit. And this is the neutral axis. What is the eccentricity? Eccentricity is not 80. What is eccentricity? Eccentricity will become 120 because total distance is 200. 200 minus 80, 120 is the eccentricity. So eccentricity equal to 200 minus 80, 120. The effective pre-stress in the wires is 1000 Newton per mm square. It is subjected to a uniformly distributed load of 16 kilonewton per meter inclusive of self weight throughout the length. The question is, the stresses induced at the top and bottom midspan. Already discussed this. Only thing is, P is not known. What is P? P is nothing but F multiplied by area. Area of the pre-stressing steel AP F means stress in steel. Stress in steel is 1000. Area of the pre-stressing steel is 500, so it is 500 kilonewtons. And you can compute area, Z, P by A, everything. It is routine. P by Z, etc. And finally, you will get the stress at the top. Stress at the top here is minus. Minus indicates that the nature of the stress is tensile. And positive indicates that nature of the stress is compressive. That's one problem. Another, if the resultant stress induced at the top and mid-span section or okay, it is also similar to that. Now, a pre-stressed concrete beam of size 200 by 400 mm is pre-stressed with 15 wires of 6 mm diameter located at 80 mm from the soffit. 80 mm from the soffit means eccentricity is not 80, it is something different, which is 120 mm. The modulus of elasticity of concrete and steel and concrete are 210 and 35 respectively. If the wires are initially tensioned to 1200 Newton per mm square, the loss of pre-stress due to elastic deformation of concrete. Loss due to elastic deformation of the concrete, what is the loss? Loss will be equal to alpha multiplied by Fc. If you understood this equation, this relation, then go for finding the alpha. Alpha is Es by Ec, which is 7. Fc means stress in concrete at the level of pre-stressing steel. At the level of pre-stressing steel. So that is P by A plus PE by I into Y. So eccentricity is known, area you know, I BD is cubed by 12. It is a rectangular section, BD cubed by 12. And Y, what is Y value? Distance of the cable from the neutral axis, that is also 120. Y is also 120. And area of the pre-stressing cable, 15 cables are there. Each cable is of 6 mm dia. It is given along with the question. You can look at 15 wires of 6 mm dia. So total area of the pre-stressing cable is 15 into that. And the initial pre-stress is 1500. It is also given in the question. It is also given in the question. Sorry, here it is 1500. Initial pre-stressing stress in the cable 1500 Newton per mm square. So now what you do, pre-stressing force means F naught into AP, you will get pre-stressing force, and afterwards find out FC. FC equal to P by A, P into E by I into Y. Accordingly, you will get 13.25 is the stress. What is the loss of stress? Alpha into Fc, you will get it. Sometimes the question may be, what is the percentage loss of stress? Sometimes, what is the percentage of loss? Sometimes the question may be, what is the percentage of stress existing? What is the percentage of stress existing in the cable? What is the percentage of stress existing in the cable? That is 92.27%. That is 100 minus this. So question may be in any form, you need to answer accordingly. The next one, the question is same. Here the entire data is given. The question is the shrinkage strain in concrete is 300 into 10 power 6. ECS is given. Size CS is given. If the wires are initially tensioned to 1200, the loss of pre-stress due to shrinkage of concrete. So sometimes the question may be with a lot of data, but you need to answer the question, what is the loss of pre-stress due to shrinkage? Because of the shrinkage, it is size CS and ECS. Knowing the value of the strain and modulus velocity, it is 63, that's all. No need of eccentricity, no need of pre-stressing stress in the cable. All these things are not required for us for computing this particular problem. So only that relation you should know. Next one. The same problem here, the creep coefficient is given. The problem, everything is same as previous one. Creep coefficient is given. Question is, what is loss of pre-stress due to creep of concrete? Due to creep of concrete, what is the loss? Loss will be phi into alpha into Fc. Already Fc value you know, already alpha value is known, phi is now 1.6, just multiplication. So this entire procedure is now repetitive. This entire procedure is repetitive. Ultimately, this is important. Alpha, phi alpha Fc and multiply it. If necessary, find out the percentage of the loss of pre-stress due to the creep of concrete. So now let us go for previous gate questions, some of the previous gate questions. This question appeared very recently in gate 2020. Gate 2020. A simply supported prismatic concrete of beam, a simply supported prismatic concrete beam of rectangular section having a span of 8 meters is pre-stressed with an effective pre-stressing force of 600 kilonewtons. The eccentricity of the pre-stressing tendon is 0 at the supports. You can look at here, 0 at the supports, and varies linearly to a value E at the midspan. So eccentricity is E. In order to balance word is important. In order to balance an external concentrated load of 12 kilonewtons, external load 12 kilonewtons applied at midspan, the required value of E minimum rounded off to nearest integer, not decimal, integer of the tendon is. What is E? So here what you want to understand, it is a balancing concept. So what is the bending moment? Since it is concentrated load, WL by 4 is the bending moment, and moment due to pre-stressing force is P into E. And substitute all the values, you will get 0.04 meters, and it is 40 millimeters. That's all about the question. It will take only half a minute to solve the problem, and it is a very recent question in the examination. Now, next question. A 6-meter long simply supported beam is pre-stressed as shown in figure. So neutral axis is given, pre-stressing cable is provided here as a straight cable with an eccentricity of 50 mm. The beam carries a uniformly distributed load of 6 kilonewton per meter over its entire span. Uniformly distributed load. If the effective flexural rigidity EI and the effective pre-stressing force is 200 kilonewtons, the net increase in the length of the pre-stressing cable is, what is going to happen in this particular case is, because of the load acting on it, so the bottom is under tension, top may be under compression. What is going to happen is, the original beam is going to extend like this. The original beam is going to increase like this. So what is that it is going to increase? Because of the tension at the bottom, final tension at the bottom, compressive at the top, after the application of the load, what is going to happen here? The bottom 6 meters is extending to 6 point something. The span is 6 meters. 6 meters is extending to something at bottom, whereas at the top, the length is reduced. The length is less than 6 meters, a small amount less than 6 meters. Okay, so what is going to happen? How the bar is going to increase? This steel reinforcement, this pre-stressing steel is also going to increase this much. You can look at here, the pre-stressing steel is also going to increase by that small distance, So what is that distance? Slope at that point, slope at that point is theta, if you call it theta, and this is 50 mm. This is 50 mm. E. So what is the delta L value on one side? One side extension of the steel is the slope multiplied by 50, theta multiplied by 50. What is that theta value? Or otherwise you can call it as E into theta. E is 50 mm, theta is theta value, so delta L will be equal to E into theta one side. That means the extension of the cable is E theta. Similarly, the extension of the cable here also E theta. What is the total increase in length of the cable? Total increase in length of the cable is 2E times of theta. So eccentricity is given 50 mm. 2 you need to find out theta. So what is that theta value? The overall slope of the member. Because of the pre-stressing, because of the pre-stressing, because of the pre-stressing, the beam is going to take the deflection like this. Beam is going to take the deflection like this. So when you compress it, what's going to happen when you compress it? This is the member. When you compress it, what is going to happen? It is going to take the deflection like this. So the deflection shape is in this way. The forces are acting or moment acting here will be P into E. P into E. When a moment is acting, what is the slope? Slope is ml by ei. ml by ei. ml by 2ei. m is pe. ml by 2ei, and accordingly this is the slope. ml by 2ei. And another one is because of the loading. When the loading is acting, that is uniformly distributed load, and the theta is clockwise. That theta 2 is, the formula WL cubed by 24 EI. Substitute all the values, you will get this in radians. So one slope is clockwise, another slope is anti-clockwise. What is the net slope? Difference of these two. This is the difference of these two. And what is the net increase in length of the pre-stressing cable? Already I told you it is 2 times of E into theta. So to know, eccentricity, now theta value also, Accordingly, the increase in cable length is 0.12 millimeters. So it is a combination of strength of materials and also pre-stressing concrete, pre-stressed concrete. Let's see one more question. A simply supported rectangular concrete beam of 8 meters has to be pre-stressed with a force of 1600 kilonewtons. The tendon is of parabolic profile. Having zero eccentricity at the supports. You can see zero at the supports. The beam has to carry external uniformly distributed load of intensity 30 kilonewton per meter. Neglecting the self-weight of the beam, the maximum dip of the tendon at the midspan to balance external load is, remember here balance is important. To balance, what is the equation? P into E, effective pre-stressing force P into E equal to WL square by 8, and accordingly you get the value of the required thing. What is the question here? Okay, no, not required. Only this is the only important thing. No need of substituting all those things. P into E equal to WL square by 8. P into E, WL square by 8 is 2240, and accordingly you will get 150. So this is a direct question. Just now we had complete discussion on load balancing concept in the previous problem also. So, okay, like that, there are some more problems. Okay, actually, I have to finish this topic by today, but I will take a few minutes, 15 to 20 minutes tomorrow at the beginning for completion of all numerical problems in the loss of prestige and the remaining in the analysis. And afterwards, I will switch over to another topic, part and CPM. That is construction management part. I'm going to handle tomorrow after 30 minutes or 15 to 30 minutes after completion of this. So, okay, so tomorrow I'll first finish the entire pending problems in precious concrete. Then I will switch over to part CPM topic. So today I'm closing now. Thank you very much. హలో క్లోజ్ చేస్తున్నానమ్మా. ఓకే.